Okay, this is a supplement to Outcome 30. We'll talk a little bit about equilibrium. So in these reactions, we're for weak acids, for example, water, which is a weak acid and a weak base. What we're doing is this double arrow means a dynamic equilibrium, which we have, for example, H3O plus OH minus, aqueous, liquid, and liquid. Alright, so you're familiar with this. This means the reaction goes two ways. The water reacts and produces H3O plus and OH minus, and the H3O plus and the OH minus, when they collide, react to form two water molecules. So you have both reactions going on back and forth continually, hence the double half arrows. So we have a way mathematically of describing this, and it's called the equilibrium constant. It's given for water, it's really given the symbol KEQ, but special equilibriums have special symbols. For example, for water we call it KW. It's the water equilibrium constant, sometimes called the water autoionization. And Ks are typically defined as the concentration of the products, in this case H3O plus, times the concentration of OH minus. So those are the products. To their stoichiometric coefficients. Well, the stoichiometric coefficient for OH is 1, so we don't normally put it in there, and for H3O plus it's 1, okay? Divided by the concentration of the reactants. This is not the real definition, but it's a freshman definition. If you take analytical, you'll learn the real definitions. And the H2O is squared because there's two of them. So that's just, it's really 2H2O reacts to give H3O plus and OH minus. But this is a pure liquid. So pure liquid has a concentration of 1. Not true, but that's how we're going to deal with it in this class. So for us, the KW, the mathematical expression is the concentration of H3O plus times the concentration of OH minus, and this is well measured. This is equal to 1 times 10 to the minus 14th, and you're expected to know that. Alright, so let's look at some other equilibrium. Leave me erase this. Okay, so here's, for example, a weak acid in water. HF plus H2O is in equilibrium. Now this is aqueous, this is a liquid, and you should know this equilibrium. We get F minus aqueous plus H3O plus aqueous. So the equilibrium expression for this, KEQ, and this is going to have a special name too. Since this is an acid, that we're starting out with an acid, we're going to call it Ka. Ka is equal to the concentration of the products, that's the F minus, to its stoichiometric coefficient, which for these are all 1, and we're not going to put that 1 in, I'm just putting it in to show you. H3O plus to its stoichiometric coefficient, that's a coefficient right there, which is 1, divided by the concentration of HF, and this is not a pure liquid, it's aqueous, to the first power, times the concentration of H2O, which is considered a pure liquid, that's why we have the liquid in there, to the first power. So the concentration of any pure liquid or solid is 1, so this whole thing goes to 1. So we get Ka is equal to the concentration of F minus times the concentration of H3O plus divided by the concentration of HF. And in your table they have a list of Kas. If I look it up here, the Ka for HF is 7.2 times 10 to the minus 4th. So once again, this is a case of dynamic equilibrium. The reaction up here at the top is going both ways simultaneously, and you can see from the value of this that the concentration F minus and H3O plus has got to be pretty small. If HF is 1 molar, this got to be 10, F minus got to be 10 to the minus 2, and H3O 10 to the minus 2, just to give us 10 to the minus 4. So these reactions do not go very much. So that's Ka. I'll do one more. Let me clear it. Let's just do NH3 plus water to give us NH4 plus OH minus, aqueous, liquid, aqueous, and we'll call, this is another equilibrium constant, which we're going to call Kb because we have a base here. So Kb is going to be equal to the concentration of NH4 plus times the concentration of OH minus to the first power, but anything to the first power is that thing, so we don't put that in, divided by the concentration of NH3 to the first power times the concentration of H2O to the first power, which is 1. It's really activity is 1. So that's our definition of Kb. And if I look up the Kb for this on our cheat sheet that you're given on the exam, it's 1.8 times 10 to the minus 5th. Okay, so that is what we define as equilibrium constants.